Okay, so where were we? So last time I proved for you guys Soslavsky's theorem, right? And Soslavsky's theorem allows us to compute the number of regions in an arrangement in a very slick, simple way, where you can forego visualization in 4 dimensions or 7 dimensions, and you can just do this combinatorial game and get the number of regions. This, of course, depends on knowing how to compute these characteristic polynomials of arrangements or matroids, and so, I mean, so far we've seen that it's a little bit difficult to compute characteristic polynomials. We have a couple of formulas for them, and for small arrangements these formulas work. But for more difficult arrangements, it's difficult. So with the tools that we have so far to compute characteristic polynomials, and so today what I'm going to do is show you my favorite method for computing characteristic polynomials. It's this amazingly powerful method called the finite field method. For computing the characteristic polynomial of an arrangement. That's the plan for today. And I'll go ahead and state it for you. But maybe before stating it, let's do an example of how it works. Let's say that you have an arrangement, and the arrangement is maybe x equals 0, y equals 0, x plus y equals 1, and x equals y. Okay. And so you draw this arrangement. This is y equals 0. This is x equals 0. This is x plus y equals 1. And this is x equals y. And so this is the arrangement. And we have one method for doing this, which is to compute the intersection poset, and then find the Mobius function, and then compute the characteristic polynomial. So if you do that, then here's R2. Here are my 4 lines, 1, 2, 3, and 4, and then 1, 2, and 3 intersect in a point, and then the others look like this. And then so this is the intersection poset. We compute the Mobius function, which looks like this. Then add up across rows. So we get a 1 here, a minus 4 here, a 5 here. And so we get the characteristic polynomial, q squared minus 4q plus 5. Okay. So that's not too, actually that's pretty easy for a small arrangement. But let me show you a different way of doing this. Let's say that, I mean, this is in R2. Let's draw the same arrangement, but now let's do it in a finite field. So each one of these equations still determines a hyperplane over the finite field. Now to make things concrete, maybe I'll draw the finite field with 5 elements squared. And so this is going to look like a 5 by 5 grid. This is the point 0, 0, 1, 0, 2, 0, so on, 0, 1, 0, 2. The idea being that you go 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, but 5 is equal to 0 in this field, so you wrap around. Okay? So for example, these 5 points that I just mentioned are the line x equals 0. They're the points that have coordinate x equal to 0. And so this is one of my hyperplanes. The hyperplane x equals 0. 3. Hyperplane 1 looks like this. These are the points with y equals 0. Hyperplane 2 is the points where x is equal to y. So those are 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4. So that looks like this. This is hyperplane 2. And then hyperplane 4 is x plus y equals 1. So you're looking for the points whose x and y coordinates add up to 1. So here's one of them, 0, 1, 1, 0. And actually, the way to do this is you're going in this direction, and you wrap around and you end up here. And for example, this is the point 2, 4, where the coordinates add up to 6, which is equal to 1 mod 5. So 2, 4, 3 plus 3 is also 6, and 4 plus 2 is also 6. And so the last hyperplane looks like this. Okay. I want to emphasize that the hyperplanes are not these sausage things. The hyperplanes are a discrete set of 5 points, right? And this is kind of a visual aid to see that they line up nicely in a way. But the hyperplane just is point, 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 point. Okay.
Federico, what were the 5 points in 4?
So there's 1 here, 0, 1, 1, 0, 2, 4, 3, 3, and 4, 2. The finite field method says you're going to look at this picture, and you're going to compute the number of points on no hyperplanes. So in this case, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But you're going to do it supposing that this is FQ. So this is a Q by Q array. So we're going to do that. The number of points in FQ squared on no hyperplane. Let's count them. So there's different ways of proceeding, but one possible way of doing it is let's just start with all of them and then start subtracting points. So here's all the points, Q squared. Now let's subtract the points on line 1. Now you guys noticed in the homework that you just turned in last time that lines here have Q points each. You proved this. And so line 1 has Q points. So on hyperplane 1. Now let's subtract the ones that are on hyperplane 2. How many are there? Well, on hyperplane 2, which is this one, I have Q points, but I already subtracted one of them. So let me not subtract that one twice. Let's subtract the other Q minus 1. These are the points that are on 2, but not on 1. Okay. Now let's subtract the ones on hyperplane 3. So hyperplane 3 is this one. There's Q points, and I already subtracted 0, 0. And the other ones I have not subtracted. So I subtract Q minus 1. And these are the points on 3 and not 1 and 2. And finally, let me subtract the points on the 4th hyperplane. The 4th hyperplane has Q points, and it intersects each one of the other 3 in 1 point. So the 4th hyperplane intersects 3 in 1 point, 1 in 1 point, and 2 in 1 point, which I already subtracted. So I need to take those 3 away, and I get Q minus 3 points that are on 4, but not on 1 through 3. Okay. I compute this, and I get hopefully the same answer. Q squared minus 4Q plus 5. So this is no accident. This is the theorem. This is a theorem of Crapo and Roda from 1970. But it was only recently that people realized. I mean, this was proved kind of theoretically in 1970, but it was only people started to use it later, and it was mainly Athanasiadis and his thesis in '96, who realized that you could actually do this to compute characteristic polynomials. So the idea is this: you have an arrangement in the arrangement that you start with is maybe in R to the n or Q to the n or C to the n, or Basically, what you need is a field that contains the rationals here. Usually, we care about either the reals or the complex. Here's an arrangement. And there is one thing that we need to ask for here. We want to take these equations and interpret them in mod Q. And if we want to do that, then these guys better have integer coefficients. If you had an equation x equals pi here, you could not interpret that in FQ because pi does not live in FQ. So we're just going to demand that the equations have rational coefficients or integer. Of course, if you have an equation with rational coefficients, then you can multiply by the common denominator and get integer coefficients. So let's assume that the equations have integer coefficients. And so let's do that. Let's call this second arrangement A sub Q. Just A sub Q is the arrangement that you get by interpreting the same equations mod Q. The arrangement with the same equations mod Q, where Q is some prime number. Okay. Then the characteristic polynomial of the arrangement that you're trying to compute is just the number of points in FQ to the n that are on no hyperplane of this arrangement. On no hyperplane of AQ. Okay. This is the finite field method. And I want to add a condition here, which is that this works for Q large enough. And we will see what that's about. But basically, if you choose a Q large enough, you can do this. Okay? So my plan for today is to prove this for you and show you how to use it.
Federico?
Yeah?
I don't understand that how does the number of points get into that equation?
So let's see how this theorem describes exactly what I did here. I started with an arrangement in R2. And my arrangement has integer coefficients, which means that I can consider the arrangement with the same equations mod Q. So instead of R2, I'm living in FQ2, okay, the plane over the field of Q elements. And I said, okay, each one of these hyperplanes becomes a little sausage-shaped thing here. And I said, all I have to do now is, in this picture, count the number of points that are on none of these hyperplanes. But Q is a variable here. I mean, I drew the case Q equals 5 so I could draw it, but Q is a variable, and that's where the variable comes in, because we're computing a polynomial in Q. And Q is a variable, which is the size of this grid. But for any size of this grid, we can make this computation. We say the grid has Q squared elements. We subtract the Q elements in 1, subtract the Q minus 1 elements in 2 that are not this one, subtract the Q minus 1 elements in 3 that are not this one, and then this diagonal has Q elements, and I already subtracted, this fourth hyperplane has Q elements, and I subtracted this one, and this one already. So I needed to subtract Q minus 3. And so what I did is basically take all of the points and subtract the ones that are in some of the hyperplanes, and this is my answer that I get. And so what the theorem says is that for Q large enough, this computation works and tells me that this is the characteristic polynomial of my arrangement. Okay.
Well, like in the first one, all, what does that refer to? The points that are not on
For there's 25 points when q is equal to 5. But that's why I'm saying that q is a variable here. So for if q is equal to 5, I have 25 points here. But if I had q points here, then I would have q squared points, which is so these are all the points in fq squared.
Oh, I see. Where Q stands for.
And q is the size of this grid, basically. Let's see some more examples.
So, keep going.
You sure?
Well, it's for q large enough, but then q is indeterminate. I mean, and then we're going to plug in -1 for it. So I'm just confused how plugging in for q and q having to be large enough are going to work together. But maybe I just need to see more before I can go.
Yeah.
So they don't overlap.
I agree, and we will see what this q large enough is about.
Okay.
This should confuse you, especially because I'm saying this is a polynomial and this is a counting problem. And so what I'm saying is that somehow the answer to this counting problem agrees with this polynomial for q large enough. And so what we're going to do in practice is solve this counting problem. And we're going to see that for q large enough, we're going to get a polynomial answer. Here, for any q, we got the same answer. For any q, we got q squared minus 4q plus 5.
Is it because if you had like 40 hyperplanes here,
But
Might just overlap like
they
that.
just might overlap too much in a small q kind of thing?
actually, let's do this in fq in f2 too,
Okay. Yeah.
because I think that's going to go wrong actually.
Yeah.
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 It's already gone wrong.
You just get 0.
In f2 too, here's hyperplane 1. Sorry, here's hyperplane 3. Here's 1. Here's
Yeah.
2.
Yep.
And then I covered everything, and now 3 is the same one as this one.
Two, yeah.
No.
No.
3 is
Two
3 is
and
actually
four.
this one.
These are
Yeah.
together.
Right?
4, but yes.
Yeah.
So what goes 4, right? So what goes wrong? Well, then I do have q squared points. Then when I subtract 1, I do have q points to subtract. When I subtract 2, I do have q minus 1 points to subtract. When I subtract 3, I do have q minus 1 points to subtract. And when I go to subtract 4, this guy tells me to subtract q minus 3 points, which is minus 1.
Yeah.
The point is that this is true if the line had more than 3 points, then you subtract 3 from them. But this line had 2 points, so how can you subtract 3 from them?
Yeah.
And that's basically what's going to happen is for q large enough, you're going to get the same answer. But sometimes for q small, there's some weird overlaps that only happen accidentally because q is too small.
So there's eventually, for some q, after some q prime, they're all going to be the same.
Exactly. Eventually, after some q, you're just going to get some polynomial, and that polynomial is going to be the answer. And that's the polynomial we're looking for. But for f2, this doesn't work because the characteristic polynomial evaluated at 2 is 2 squared minus, so 4 minus 8 plus 5 is 1. Yet, there's 0 points in my f2 squared minus the arrangement. And this is basically what's the kind of thing that's going to go wrong. Okay, okay, so let's just compute. Before I prove this, I'm going to prove this for you, but I want to justify to you that this is really extremely useful. And so I'm going to show you how useful this is by computing explicitly some characteristic polynomials. For example, let's consider this arrangement. It's an arrangement in Rn, and it consists of the coordinate hyperplanes. x1 equals 0, x2 equals 0, and so on until xn equals 0. Okay. If I try to draw this, I'm going to fail. Maybe I can draw it in 3 dimensions, and that's about it. What's the old way of doing this? Well, we have to compute the poset of intersections. You can do this. If you intersect x1 equals 0, x3 equals 0, and x7 equals 0, you're going to get the subspace x1, 3, and 7 are equal to 0. If you do this carefully, you're going to find that the intersection poset is actually one that we're familiar with. Here's the empty intersection, then here's endpoints, then any two of the hyperplanes intersect, any three intersect, and the intersections are different, and so on until in the top you get everything intersecting. In other words, this is a poset that we know. It's 2 to the n. You should think about this. This shouldn't be immediately obvious, but it is true. And in the homework, you guys computed the Mobius function of this guy. It goes 1 minus 1, 1 minus 1, 1 minus 1, which means that the characteristic polynomial is 1s here, then minus 1s here, then so this is the summation of, in the ith level, you have n choose I guys, q to the I, and then minus 1 to the I. And this is q minus 1 to the n. I'm doing this too quickly, but I mean, the point is we know how to do it. It's a little bit complicated, but we know how to do it. Okay. But let's see how to do it using the finite field method. The finite field method says these are the points in fq to the n that are on none of these hyperplanes. That means that they don't satisfy any of these equations. That means that the first coordinate is not 0, the second coordinate is not 0, the last coordinate is not 0. So here's the counting problem. Find the number of points in fq to the n where no coordinate is equal to 0. How many are there? Well, you need n coordinates, right? First coordinate, second coordinate, third coordinate, so on until the last coordinate. Now, how many choices do you have for the first coordinate? Well, you would have q choices, except you're not allowed to choose 0. So this guy has q minus 1 choices. Then again, here you can choose anything that's not 0, q minus 1 choices, and so on. For the last coordinate, you choose anything that's not 0, q minus 1 choices. So therefore, the number is q minus 1 to the n. This is way easier than this. Okay, so that's my first example. So that example is a little bit impressive because we can do something that we already knew how to do in an easier way. But now let me show you an example that really was very difficult. Again, I'm going to consider an arrangement in n dimensions. And this is called the Braid arrangement. This is an arrangement in Rn. People usually write it Bn, and B is for braid. And what you do is that in Rn, you consider, for each pair I and j, you consider the hyperplane xi equals xj. Okay? I hope this looks familiar to you. So
This like corresponds to the
the normal vector to this hyperplane I mean, again, what is the old way of doing it? You find the intersection poset. And actually, you guys did this in your homework. And you found that the intersection poset for this guy is is the partition lattice. Okay. Each one of the hyperplanes contains two variables I and j, and this is one of the atoms in pi n, which says merge I and j. Now, when you intersect the hyperplane xi equals xj and the hyperplane xj equals xk, that means xi, xj, and xk are going to be equal, which means the block ij and the block jk are merged into one block ijk. And if you do this carefully enough, you're going to see that the intersection posted is the partition lattice. So the partition lattice, we saw it. It looks like this. Here's the bottom. Here's the top. The bottom looks like this. The top looks like this. And then the next thing you're supposed to do is find the Mobius function. Okay? And you saw that the Mobius function is not the first thing you would want to compute. I mean, you did it, right? And you got an answer, and the answer is kind of nice, actually, when you get to it. But you saw that this is not easy, and it's messy. Messy Mobius function. Okay. And then you're supposed to take that and just add up according to the floors and get the characteristic polynomial, which is a big sum of all these messy numbers. And so, a priori, you're going to think you're going to get a mess. Right? You're taking a bunch of individually messy things and adding a lot of them. You should get a huge mess. This is a huge mess. It's not just a mess. But yet you did this. You did this, and did you do this? Mm-hmm. So you did this, and kind of by magic, you just get these messy, horrible things. They're not horrible, but they're messy. You add up, and it turns out you just get this polynomial, q minus 1 up to q minus n plus 1. And this, I think, was kind of shocking to you guys when you got this, and then you said, okay, how do I prove this? And you proved it, and the way you proved it was kind of putting together a bunch of homework problems. So you had to put together the homework problem that said this, that the partition lattice is the lattice of flats of the complete graph. Then you had to take the exercise that said that, I guess it was the last exercise in this homework, that said that it told you how to compute colorings in a graph. And then once you did that, you said this was the number of colorings in a certain graph. So we did it, okay, but first of all, it was a lot of work, and second of all, it really took a lot of direction. Here's one thing, here's another thing, here's another thing. It's not something you would just kind of come up with on the spot. Okay, but let's do it now using this. So what's the characteristic polynomial? We're supposed to compute the number of points in fq to the n that are no hyperplane. In other words, no two coordinates can be equal to each other. xi is never supposed to be equal to xj for I and j distinct. Okay. So again, what are you supposed to do? Well, we're supposed to pick the n coordinates. And you're going to say, what can I put here? Well, I can put anything. Over there, I wasn't allowed to put coordinates equal to 0, but here I can put anything. Q choices. I can put any coordinate. Over here, what can I put? I can put any coordinate that is not equal to this one. So out of the Q coordinates, I can choose any one except for the previous one. What about this one? Well, I have Q choices, but I'm not allowed to repeat this coordinate or this coordinate. And these two are different coordinates. So here I have Q minus 2 choices. Dot, 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 dot. Here, I have q choices, but I'm not allowed to use any of these coordinates that I already used. And these are all different. So I have q choices, but then n minus 1 of them are eliminated. So in the end, you get q times q minus 1 times q minus 2 dot 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 times q minus n minus 1, which is the formula. So if you know this, this is really a completely straightforward exercise. If you don't know this, then it's really a serious, difficult problem. Any questions about either one of these two computations?
So this feels to me like it is exactly what we did with the complete graph. I mean, like if you translate that hyperplane arrangement to the graph, then the reasoning that you used here is the same reasoning that we used just on the points, the vertices of the graph. Is this? But it feels like this theorem is sort of fundamentally bigger than the theorem about the colorings of the graph. How does this like, I don't know. I don't even have a question yet exactly. I mean, it's just sort of the question. I mean, my question is sort of: is this theorem encompassing a lot more than that?
So Kim's question is: this sounds very similar to the arrangement, to the argument of coloring the graph. So can I say something more general? Well, so let me define a graphical arrangement for you. You start with a graph G, and you're going to make an arrangement. Okay? And it's going to be exactly for each edge ij, you're going to put the equation xi equals xj. So if you give me a graph, then this is called the graphical arrangement of the graph. And it's written A sub G. So if my graph looks like this, 1, 2, 3, 4, then the graphical arrangement has x1 equals x2, x1 equals x3, x1 equals x2 equals x3, and x3 equals x4. This is the graph. And this is an arrangement in R4. Okay? So let's use the finite field method for this arrangement. It tells me the characteristic polynomial of my arrangement is the number of points in fq to the n on no hyperplane. Okay, so that means in this case, you want to choose coordinates x1, x2, x3, and x4, and they shouldn't satisfy any of these equalities. So a no hyperplane means such that xi is different from xj whenever you have this equality. In other words, whenever you have an edge. This is what the finite field method says. You're supposed to count points in fq to the n such that the coordinates on an edge disagree. Okay, well, what are the names of your colors? Then you're going to call your colors 0, 1, 2, up to q minus 1. So what you have to do is instead of a color, now we're assigning a number between 0 and q minus 1 here, with the stipulation that whenever you have an edge, the numbers I assign to the vertices are different. So what we're doing here is exactly coloring the graph properly. This is the number of proper colorings of the graph with colors 0, 1, up to q minus 1. And so, Kim, you're absolutely right. Not only is it similar, really what I'm showing you here is that this theorem is a generalization of your homework question. Your homework question said, prove this. And it was hard. It might have been the hardest question in the homework. Well, if I had given you this, then it would be immediate. Okay, so I think that justifies that theorem. I think this shows you this is a good theorem, and we should care to prove it. Seems very useful. So how am I going to prove this theorem? Well, again, let's imagine that you're maybe in R3 so that you can visualize what I'm going to do. And if you remember last time when I was doing some argument about Euler characteristics, what I said is let's take a slice of the arrangement and see what we get. So let's do the same thing here. Here's my arrangement in R3. And let's take it, imagine that the whiteboard is one of the planes, and let's look at the slice on the plane. So here's a flat of the arrangement, and let's say that it looks like this. This is a slice of the arrangement along a flat. And now let's look at the same picture, but in FQ. So in FQ, this looks like this. Each one of these lines is now a discrete set of points. They kind of look like this. And so this is maybe the flat Q in the arrangement A sub Q. Okay. Now what I said last time is let's look at these guys. We call these guys G1, G2, G3, G4, H1, H2, H3, and H4. Each one of these guys is going to translate into the equivalent thing here. So G1 becomes this line, G1 sub Q, and so on. The point H1, for example, becomes the point H1 sub Q, and so on. And what I'm going to do now, remember so far this is exactly the same argument that I did last time. And I said, what I did is I said, let's compute the Euler characteristic of the flat. Well, now instead of computing the Euler characteristic of the flat, I'm just going to compute the number of points on the flat. Okay? So number of points in, but of course, number of points here because I want a finite answer. Number of points in the flat sub Q. How many are there? How many points are there on this flat?
Q squared.
It's Q squared, and And the reason is that still, any two-dimensional plane in FQ to the n has q squared points. In general, any, so q squared. This is a two-dimensional plane that has q squared points over a finite field. But now I want to say, let me count them in a different way. Let me count them by separating them into groups. First, I'll count the ones that are not on any of the G's or the H's. Number of points in FQ, no. In that notation, isn't it? Be careful when I say F without script, I mean this flat. And if it's with script, that means the field. Number of points in FQ is equal to the number of, first let me take the ones that are in F and not in the G's and not in the H's.
Aren't all the H's in the G's?
Yeah, so of course if it's in an H, then it's in a G. How many are there? Well, we just did this. Okay, erase it, but we just did this, and we got q squared minus 4q plus 5.
Oh, right.
It's the same arrangement as before. It's just kind of tilted over. Okay, so this is q squared minus 4q plus 5. So I already counted the ones that are on none of the planes, but I'm missing some. For example, I'm missing the ones that are on G1. So let me add those. Plus number of points that are in G1. But let me count only the ones that are on G1, but not on the H's. Not in H1. Not in the H's. How many of those are there? The points that are on G1, but not on the smaller things. Well, G1 has q points, and I need to subtract this one and this one. So q minus 2. Okay, so I keep doing this. I add up the ones in G2 and not in the smaller things. Then the ones in G3 and not in the H's. And then the ones in G4 and not in the H's. So in G2, G2 is this one. So it has q minus 2 points. G3 is this one. So it has q minus 2 points. And then G4 is this one. And it has q minus 3 points. So I counted the ones that are on no hyperplane, the ones that are on G, on any of the G's. Now I need to add up these 4 guys that are on the H's. I haven't counted those. So plus number of points in H1, plus in H2, plus in H3, plus in H4. Okay? And of course, each one of these things is 1. 1, 1, 1. Okay? And so I get an identity that says q squared is equal to q squared. Okay, when you do this, you see that you get an equality. What am I saying in general? Well, I'm saying in general, if this guy was d-dimensional, then a d-dimensional space here has q to the d points. So this guy has q to the dimension of f. This is the number of points in f sub q. And I just separated them into groups. What are the groups? The groups correspond to F, G1, G2, G3, G4, H1, H2, H3, H4. In other words, F is a flat, and the different groups correspond to the flats that are inside it, which are the flats that are higher in the poset. So for all the flats that are higher in the poset, I'm counting the number of points which are in the flat GQ and not in any higher flat. Okay. And we're used to this by now. Whenever you have this calls for Mobius inversion. Here you have a function of f, and you're adding over the g is bigger than f, a function of g. So this is my first function in Mobius inversion. This is my second function in Mobius inversion. And now let me apply the inversion. So I apply Mobius inversion. Which tells me that the number of points in the flat FQ and not in any higher flat is equal to, Mobius inversion tells me I should add over the g is bigger than f. I put the other function here, q to the dimension of g. And then I just put the Mobius number here. Okay. But you see, what is the right-hand side here? The right-hand side is the number of points which are in the bottom flat. The bottom flat is fq to the n, and are in no hyperplane. They're not in the higher flats. So this expression that I have right here is exactly this expression for the bottom element. So maybe I'll just say the bottom element. I get number of points in fq to the n, but not in any higher flat. And of course, if I say that it's not in any hyperplane, then it's not going to be in anything else. Then I'm supposed to plug in f equals 0 here. So now I'm adding over all the g's that are bigger than 0, which are all of them. So all the g's in the lattice of flats of mu of g times, and just like last time, the dimension of g is r minus the rank of g. And this is exactly the definition of the characteristic polynomial. So there it is. Any questions? Two things. Let me make two comments. The first comment I'll make is that you should now go back to your notes and compare this argument and the argument from last class about Mobius, about Euler characteristics. And you'll see that it's basically the same argument, except that instead of q, I have -1. Here I used this for q. And if you just take all the q's and make them -1s, then you're going to get exactly the same proof that I gave last time. So are you supposed to think that Euler characteristic is kind of like counting in a field of -1 elements? Maybe there's something to this. Actually, there's a paper about this that I'll show you guys if you're interested. But that's one thing, that it's almost eerie that it's exactly the same argument we did last time, and yet it seems like we're doing something very different from last time. That's one thing, the first comment I'll make. The second comment I'll make is that actually we're not done. And why are we not done with this proof? What have we not addressed in this statement? Where did I ever use that Q was large enough? This should be suspicious if I gave you a proof that didn't use one of the hypotheses. And if you look carefully, you're going to see actually that this matches this, but this doesn't match this. Because that's the characteristic polynomial of A, and this is the characteristic polynomial of A sub Q. And so what do you have to do to finish? Well, you have to basically guarantee that for Q large enough, A and AQ have the same characteristic polynomial. So the last thing to check is that if Q is large enough, then A and AQ have the same characteristic polynomial. And the reason is that they have the same intersection poset. And because they have the same intersection poset, the characteristic polynomial comes from the poset, so they have the same characteristic polynomial. And I don't have time to show you guys this step, but this is on the notes, so you can see how you prove this. The point being that when you're in the wrong field, the equation might degenerate. For example, you could have an equation 2x equals 0. Well, that's a hyperplane, but over F2, that's not a hyperplane. And that's going to ruin the intersection poset. And the point is that if you go to a large enough field, then these coincidences are not going to happen. And you can see the proof on the notes. But that concludes the proof. Okay.
That was great. Yeah.
I'm going to try to make your talk better.
That sounds perfect. Do you have any?
I won't be stressed.
Happy spring break.
Happy spring break.
Should I start using those?
Well, I have this one greedy algorithm one that I got together. I don't know if I didn't talk to you about it.
No, I don't think I got it.
This actually seems like it might be pretty cool, but that would come later, I think.
Once we figure it out.
So what it is you have some frame, and maybe you're in a 50,000 dimensional space,